Hi everyone. For those who don't know me, I'm Becky Trippier. I'm an ecosystems analyst in the ecosystems analysis team here at JNCC. So today we're going to take you through two case studies from this year's Data Science Accelerator program. So both of which are using imagery and machine learning to classify features and habitats in the landscape. So first I'll take you through my project, which is looking at peatland condition using deep learning methods. And then we're going to be joined by Georgina Vickery from UKHO, who will talk through her project on mapping the extent of salt marshes using Sentinel-2 imagery. A quick introduction to the Data Science Accelerator program for anyone who's not familiar with it. So it's a free program open to all public sector bodies, and it's run in partnership with the Government Digital Service and the Office for National Statistics, as well as having lots of data hubs around the UK. So, for instance, UKHO have one of their data hubs as well. So it's a program designed to give you dedicated time to build your data science skills, which can be things such as geospatial analysis, machine learning, or learning to create new cool visualizations. Some people start with prior coding knowledge, like myself, or some with none at all. The program is designed for learning and provides you with your own mentor from another organization. So you can talk to them as little or as much as you need to give you that kind of support. And as well as the mentor, you're also supported by a huge network of past and present participants on the program as well, who can help out with any kind of problems or share like good project management skills with you, and just provide you with a bit more of that kind of that expertise there. So you don't need to be an expert going into it at all. It's just you just need to be very keen to learn. So you get 1 day a week for 3 months set aside in your calendar, which total up to 12 days. So it's only a short amount of time, but it is great for trying out different methods, creating proof of concepts, and there's no pressure to produce anything at the end of it, just to give you that opportunity to learn something. So yeah, I can't talk up the program enough, really. So you can sign up to be either a mentor or a mentee. So the mentees, you get the benefit of that time set aside to learn something that you're interested in, be supported in your learning, and network with others across the government. For mentors, you get to learn from helping other people with their projects and strengthening those links between partner organisations you might be familiar with already, and working in similar areas and also just share your own expertise and give someone else that kind of that mentorship. And finally, it's also a benefit for JNCC just overall to help make better links with other organisations working in similar areas, as well as building our own capacity and creating new kind of capabilities and workflows, which we think can then like explore into the future. So, okay, so I thought that all sounded great. I've been meaning to sign up for quite a few years since I've been here, and finally got around to it this year. So my project, which I submitted and undertook as part of the programme, was focused on how deep learning models can help us to monitor the condition of peatlands. So peatlands are really key ecosystems, providing valuable ecosystem services, such as helping to regulate our water, providing habitat to a range of species, and are an important carbon store. 80% of our peatlands in the UK are thought to be in a damaged state due to pressures such as drainage, peat extraction, and burning. And in this state, they emit stored carbon back into the atmosphere, which is why they're so key to monitor. So monitoring of peatland condition has traditionally involved ground-based type surveys, relying on experts in the field. However, a visible indicator we can monitor using Earth observation is looking at areas of bare unvegetated peat, which can indicate sites in poor condition. So our previous efforts to do this has been using high resolution aerial photography, as they occur very fine in the landscape. They occur both as large or smaller patches, as you can see in the images, and they can look extremely variable. So these are all images which were captured in 2018 over the Peak District using the APGP service. And as you can see, they're yeah, pretty varied in their appearance. And it can particularly be challenging compared to other features which I've put on the side there, such as looking quite similar to certain types of vegetation, so things like heather, and to kind of river waters which have very heavy sedimentation. So I've been working on peat here for the last year, I think. So our previous approaches we've kind of looked at have been to use indices thresholds and shallow machine learning techniques such as random forest classification to detect bare peat, as well as the misidentification I mentioned. These methods showed that there's also a lot of variability in the underlying data, so between capture dates and regionality, differences in image quality, the angle of capture, weather and light conditions during flights can all cause lots of variation in the data. So this makes it quite a challenging process, as well as quite a manual process to digitize training polygons and determine thresholds for these particular methods. So we have a feature that can appear very variable and a highly noisy imagery dataset, which we're trying to distinguish this feature within. So deep learning methods have shown to be really powerful tools for image detection and have been used to solve even the most complex of tasks, such as this one, to determine whether a picture is of a chihuahua or a blueberry muffin. Other examples include facial recognition on your phones or chat boxes or virtual assistants. So deep learning is a type of machine learning which progressively learns patterns in your data through multiple layers of transformations to learn which elements in the image are important for defining your particular feature or classifying your image. The main difference from shallow learning methods is that it learns its classification features from the data itself, rather than requiring defined features to be fed into the model. It's quite a coarse labeling that you can do for that. So much like our brains learn with experience, the models iteratively learn and have functions to tweak the model and the data as it learns to become more accurate. Convolutional neural networks, so which CNNs in particular, are really good for image recognition, where you have lots of variance going on in your data. So these can be trained to classify images at the whole image level or within images, so down to the individual pixel or feature. So I was keen to see how deep learning could help to solve this problem, and that in the 12 days was aiming to come up with a workflow for developing a model and making predictions. So for the project, I used R for the pre-processing and labeling steps, as I use R every day, and GitHub for the version control and for tracking the project using their planning tools. For the modeling itself, I carried this out with Python, so I got to learn a bit of Python, and the Keras library, accessing a GPU through the use of Google Colabs. So the first step was to do some pre-processing of the data. So the imagery is received as 1 by 1 kilometer tiles with separate RGB and color infrared images. So I pulled out 14 representative tiles, which I thought clearly represented areas of bare peat is clearly visible, and stacked the near infrared band with the RGB image to give a 4-band image. Then each of these 4-band images was then divided up into much smaller chips, as you can see in the picture, to be able to pass that information into the model. Then each chip was labeled to say whether bare peat was present or absent within that chip. So for this, I just repurposed an old R-Shiny app to efficiently cycle through creating these labels. In total, I labeled about 3,000 chips, which took about 3 days. And so 500 of those 3,000 were then held back as a test data set to evaluate the model afterwards. So this is a little daunting, this workflow, but this so then we converted the NumPy arrays and to bring them into Python environment with Google Colabs, where we carried out a few more pre-processing steps to rescale the data and randomly shuffle it up, and then pull out the labels separately. We added some data augmentation steps. So these are things like flipping the images or rotating it, which increases the training dataset size and also helps to reduce overfitting to our images, making the model a bit more robust and able to cope with our noisy data. We then tried fitting several different types of deep learning models and evaluating the performance with a validation dataset during the training process, as well as the test data sets at the end once the model was fitted. So these are some of the results at the chip level. So the model outputs a probability of bare peat being present within each chip. I used so a few models which we created from scratch, but then also some pre-built models within Keras, such as the ResNet model and the UNet model. The UNet model we found particularly performed very highly accurately with 92% accuracy. So UNet is a weakly supervised segmentation model, and so can also output the results down to the pixel level as well. So even given our kind of weak labeling as an input, you can still get this pixel level result. So it's an example of that. Which seems to show very good positive detection of the feature and not a lot of misclassification with other features in the imagery, which is pretty good. So as well as evaluating the models with the held out data from the training area, we also ran the model to predict over an unseen area from Yorkshire. So this is Yorkshire moors captured over a similar period in 2018. And yeah, this demonstrated pretty highly accurate results as well in this unseen area, which is pretty promising and quite can show that we might be able to use this a bit more widely. So the next step for this work is actually it's going to be built into a part of the MOU we have with NIEA. So our team is going to be carrying on testing this method across the Sperrin Mountains in Northern Ireland and comparing this to the previous methods that we've trialed there. So it's nice, and yeah, this will see if the method is more transferable and how it behaves at different sites across multiple capture states and with different sources of aerial photography as well. Validating this type of method is quite hard, as you need data captured on the ground at the same time period to when the photos were taken. But we can explore what ground truth data might be available to help us to do that. And yeah, just generally some more trialing of different applications of this using different types of source data and yeah, just to see how usable it is. So just a final note about the program is, yeah, so this, after our running, it's been split up into two programs. So there's the Data Science Accelerator program and the Data Visualization Accelerator program. Applications have just gone. I tried to promote it a bit with the Code Club, but it will be coming back next year, so can always try again next year. Okay, so thanks to David Stevens from UKHO, who was my mentor for this, and thanks to other colleagues in JNCC for supporting my application. Okay, so I think we're leaving questions until the end, but please put them in the chat if you have any, and I'll hand over to Georgina. Somehow.
Yep, we can.
Thank you. So just a quick thank you to Becky for inviting me to talk to you all, because I've not really spoken externally before, so this is a really cool opportunity for me. And then just a quick note to add on to what Becky said about the accelerator program is that I can't recommend it enough. On a personal level, I really enjoyed my project, and having that one day a week just to really focus on something really helped me develop my skills with Python, deep learning, neither of which I'd actually used before. So I had some experience with R and doing stats with R and data visualization, but never with deep learning. So being paired with a mentor and given that time just to focus on it was really beneficial, and it definitely worked out well for the UKHO as well. As I'll show you later, I've actually developed a proof of concept of the ability to map saltmarsh from space, and the UKHO is seriously considering taking it on as a genuine project and a product that they'll begin to market, hopefully. So yeah, there was no losers in this project, and so I definitely recommend applying to the accelerator program. So my mentor was Tamsin Forbes from the Department of Transport, and her expertise was definitely in the data preparation and getting my data into the model. And then I was a bit more on my own. But throughout all of that, I can definitely say I achieved my overall aim of my project. I guess a lot of you probably do know a fair amount about saltmarshes and natural environments, but I'll briefly cover a few sort of facts about why they're really important before I start getting into the actual project I did. So these stats are from an ONS 2016 report. And just to pick out a few key ones that I think are quite poignant for today with the recent flooding, in that in 2016, the value of coastal fences conferred by saltmarshes was £2.5 billion, and that's only increased in the years since. And what's particularly important about saltmarsh is that they accrete over time. So with sea level rise, as long as sea level rise isn't too quick, saltmarsh can keep pace, whereas man-made coastal defences, they have to be constantly maintained and added to. So that's definitely a plus for the saltmarsh and the natural ability to protect the coasts. And saltmarshes do so much more for the environment than people give them credit for. If you can name any one ecosystem service that we get from any habitat, saltmarshes will do it, and they'll do it better than any other habitat. So bioremediation of waste, water quality maintenance, supporting fisheries, acting as a nursery ground, they're amazing. So now I've sort of told you what they do for us, you could probably thinking, well, why do we need to map them? And it's because we don't actually know how much we've got. The first point there, just 25 to 50%, that is a huge range of unknown data. That's almost bigger than the data point. And that in itself highlights how much work we have to do to try and understand what we've actually got. And another key point as well is that it takes 50 to 100 years for a saltmarsh to actually become really efficient at sequestering carbon. So the restoration work we do now won't really have a huge impact for another 100 years. So it really highlights we have to know what we've got at the moment and stop that degrading anymore as a priority. And nearly every report you read, it will always conclude we need more data, more spatial data, more temporal data, you name it, we need more data. And I'm sure a lot of you here are pretty much on board with that. And I got a really positive response from the Minister of State for the Environment, Lord Zach Goldsmith, about this project. I'll go into more of what he said later, but he basically sent me a huge list of organisations to contact, which I have since done, just generated more positive interest. And so there's a huge array of applications for this project, and the data set that I've hopefully will finally produce. I've done a lot of work trying to get to that, but it's trying to work out what the stakeholders actually want, but I'll sort of delay that in a few slides later. But just at the start, I want to go over why it's so important that we know where salt marshes are. And because if we know what we've got, we know how much we've got, well, we can trade it with carbon credits. And the next 2 points on that slide, so like monitoring and achieving targets. Salt marsh is a priority habitat under the UK government's 25-year environmental plan, which is really heavy on water quality and air purification. And salt marshes that's what they do. So salt marshes are really big in both of those achieving both those targets. And then the last point on that slide, the automation of current habitat mapping. I was speaking to Coastal Channel Observatory and talking to them again later this week. And they're really keen on increasing the automation of their current habitat mapping, because there is some automation at the moment, but not to the level that it includes deep learning. And deep learning, while it is quite computer heavy and process heavy, you can do it at much smaller temporal intervals, which actually increases the resolution, and it really helps you determine maybe change over time and other sort of aspects you're interested in. So at the moment, there's a lot of manual checking on the ground, which is still really important. But by increasing automation and using more and more aerial imagery, you can really increase the accuracy without massively increasing the cost and the manpower. And the picture on the right is actually from San Francisco, because I couldn't find a dramatic one from the UK. But there's another example where they did a similar project to that on the Humber. where they've breached man-made coastal defences to allow salt marsh to develop behind them. And that's a really good example of how you have to use huge scale monitoring, because yes, you'll create a small salt marsh, maybe several hundred hectares, but it'll have wider reaching effects beyond that area. So using satellite imagery or aerial imagery as planes fly over, and also with the increasing use of drones, is quite poignant with these such projects as well, in terms of how people are realizing salt marshes accrete over time. So as a sea defense, they're one of the best things we've got. That image just shows the levels that people will go to. They put loads of money into making these hard defenses, and then they do the research and realize salt marshes are better at doing it than their hard defenses. So just to sort of reiterate, the overall aim of my project was to do a proof of concept of the feasibility of using remote sensing data to predict salt marsh extents. I broke this down into 4 objectives. The first 3 I definitely did achieve. I created a model, I evaluated it, and I visualized it in those different ways. The 4th one I'm still working on, because as I speak to more and more stakeholders, I'm trying to see more how I can actually tailor the data that I produce to suit people's needs. So people might not necessarily want me to spit out one number for the area they define. It might be better for me to create a dashboard or to work on change over time, for example. So the 4th one is definitely evolving. So where did I get my data from to do this project? My satellite imagery, as Becky already mentioned, was from the Sentinel-2 satellites downloaded from Copernicus's Open Access Hub. I know JNCC, I recently found out you've got a portal where you've got like pre-processed data for this kind of stuff, which I've been looking into. So I'm definitely going to try and hopefully incorporate some of that. And then as well, Becky mentioned as well, for machine learning, not for deep learning as much, you need labels. Well, you do also need it for deep learning, but different types. And I got my labels from the Ocean Data View on the UN's website, and they've got a lot of different types of geospatial data from data papers. And I'd really recommend you having a look if you're interested in getting labels for any kind of similar projects, because it's not global and it's not perfect data, but it's a really good start if there's not much else there for you to use. So this is just sort of a zoomed in area of one space in Scotland that I focused on. It's called Udale, the bit on the left is. And each orange polygon shows you where salt marsh is known to be. But even looking at it from this scale, it really highlights the disparity between the number of salt marsh pixels to the number of non-salt marsh pixels. I had 4 times as many non-salt marsh pixels in salt marsh, which means my model could get a really high accuracy with saying nothing was salt marsh just because of the probability. However, I found out that later on my model wasn't doing that and it was working fine, but that was where I had to start with in the imbalance in my samples and my data. So just to zoom in on the one on the left, which is Udale, the bottom polygon was how I downloaded the data. And as you can see, it covers a lot of streams, roads, hard surfaces. So I spent a lot of time cropping the data and cutting out those hard surfaces, which definitely increased the accuracy, and it was definitely necessary to do. However, interestingly, near the end of the project, I went onto a different website and I found this, which is from Natural England's Open Data Portal, where they've done a lot of manual habitat mapping with a lot of automation built in. And it was, so this is an example further south near London of a salt marsh, where every single stream has already been cut out. So at the start, I was thinking, oh my gosh, that would have saved me so much time. But when you really look into it, salt marshes are so dynamic. So year on year, even month to month, the streams, as they worm their way through the sediment, they change the path. So what's an accurate label in one year isn't an accurate label in another year. So it's really difficult to generalize. So the more specific the label is, the harder it is to make it transferable. And you almost have to, rather than having one label for a stack of images over time, which is what I did do, and it worked fine. If I used data like this, it would have been a lot harder to almost generalize year to year with my labels. So in the end, I was kind of grateful I hadn't done this too early, but it does show there's good data out there. But this hasn't made my project redundant because this required a lot of manual work, whereas my project was a lot more automated. So getting on more into how I managed to make my model like increase the accuracy of it, I calculated indices. So similar to what Becky was saying, you see the 3, you see all the visible wavelengths when you look at a satellite image, but there's other wavelengths that are collected that aren't visible. So for example, near infrared, and through manipulating those bands, you can pull out different characteristics. So this is just a list of the indices that I calculated that I found increased the accuracy of my model. I calculated a lot more that didn't necessarily contribute that much. So if you ever do a thing like this, I'd recommend just have a play with different indices and plot them and see what they look like. These were the ones that I calculated and I found it help. So the different models I looked at for my projects, I explored sort of 5 different ones in some level of detail. The top 3 there are all machine learning, and I found random forest by far outperformed the 2 above it in terms of its accuracy, its speed, and you'll probably find that a lot in the literature as well. Random forest definitely outperforms others in machine learning. And on the right hand side, there's a really generalized view of what a random forest looks like. It's basically a decision tree or a flow chart in a way of it, trying to distinguish groups of data. So for me, it was color of pixels or the value of pixels, and split them into different groups as it classifies them. And that there's one branch of a huge tree, of a huge forest, sorry, one tree of a huge forest. And that's quite a simplified one. My actual one was way too big to put on the slide. The bottom 2 models there are both deep learning. I found UNet outperform ResNet. And I haven't actually got any visualizations of my UNet on this PowerPoint because while I've got a lot of positive numbers being spat out in terms of its accuracy and its reliability, I find it quite difficult to get an actual printout of a really pretty picture to show you all. So I haven't got that, so I apologize. But just to sort of show you some evaluation of my random forest, I found it was more likely to label non-saltmarsh as saltmarsh than the other way around, which is what I expected. But overall, across several thousand kilometers of area that I tested, it misclassified 4.4 kilometers squared, which is a big area when you think of it. But compared to the area tested, it isn't that big. So I was happy, but it also shows why I'm focusing now as well, as much as I can on deep learning, just to really get that accuracy up a bit more. But overall, on my training data, I had 99.9% accuracy. So I was already thinking, oh, is it overfitting? Is it not overfitting? But when I tested on my test data, so this is data the model hadn't seen previously, so it hadn't got anything to base its assumptions on apart from what it had learned from the training data. I had 97.8% accuracy, which was still really good. But that's something I'm still working on refining. And I had different methods of trying to refine it, including upsampling, data augmentation in my training data, and a few others, which I won't go into in this presentation. So just sort of go back over what I did achieve. I did achieve my aim, big tick. And my objective, first 3, definitely achieved. And then my 4th one, I'm still working on as I work with stakeholders and the project evolves, so I take it further. This is a quick list of the different organisations I have contacted externally and had a really positive response so far. And Coastal Channel Observatory is specifically really keen to work with the UKHO to really decrease the manual side of their habitat mapping. And these are some questions that I'm trying to answer as well. So if there's anybody here who has any sort of input or any experience working with them, I'd really appreciate any advice, because I would like to develop an interface so a stakeholder could access like an app or an interface and define an area of interest or type in some coordinates, and it will spit out like a map where they can just see a nice pretty picture of this is so much, this is how much we've got, this is quality. And talking to people are interested in being able to determine quality from space, but the more of the interest is in how much sediment has been accreted, so change over time. And that's a lot harder than you might necessarily think. It's not as simple as looking at 2 images and comparing how far it's moved, because so much will go up in elevation or in and move different to the extent, like horizontally and vertically. You have to sort of take into account. So it's actually quite difficult to do. Plus, they're so dynamic, so they will change naturally year on year, but they might not have actually accreted overall. And then the final point there is areas of concern. So I'd like to be able to focus my model and really get it going well on areas where we have a complete lack of data. So there's some areas in the UK which have got really well mapped coastlines in terms of salt marsh, for example, North Norfolk and a lot of estuaries. But there are some areas, often in Scotland or Wales, where we have a lot less data in terms of its temporal resolution as well as its quality. So if I could focus my model on that, I'll hopefully be able to sort of resolve a lot of the gap we've got between science and policymakers as well. Yeah, so just to round off with a quick personal reflection, I really enjoyed doing this project from a personal view. I felt like I've learned a lot of new skills, which I'm trying to work into my department in terms of just the process that we do day to day and improve that and the efficiencies. And the UKHO has definitely benefited in terms of me showing that it's a definitely viable route to develop a product. And the data that I'm going to produce will feed into COP26, government's 25-year environmental plan, and really help inform coastal sustainable development in the future. So yeah, thank you for listening. If you've got any questions about any of my models that I've used, anything that I've said, please don't hesitate to contact me. My email's there. Yeah, thank you very much. And I'd appreciate any input as well on the models that I did use.
Thank you very much, Georgina. Thank you very much, Becky, as well. So we've got the Jamboard up, so just make sure let us know if you don't have any access to it. We do have the 2 slides for the Jamboard, so we're trying to split the questions between the 2 presenters today. So we're going to start off with Becky. So Becky, are other agencies around the UK developing similar methods to yours for peatlands?
So deep learning methods are being used a lot more. I know from being in the EO implementation group meetings that other agencies are using it for things such as identifying burn scars in the landscape, that kind of thing. I know that EA, I think, are trying to get more into the deep learning area. But yeah, I haven't had many of those conversations, so not specifically, no, I'm not too sure.
Okay, thank you. And can this approach be applied to monitor changes in the conditions of woodland or forests?
Why not? Yeah, I mean, I think it's knowing which kind of visible indicators you can pick up with the imagery, and then yeah, having a play around and seeing if they can pick them up. For woodlands and forests, I'd imagine you'd be able to pick out kind of individual trees which are around, maybe not in a part of the forest, or possibly maybe deadwood features. Oh, bad network quality. Oh, hopefully you can still hear me.
Yep.
Okay.
Okay, and does the technique look like it will compensate for the variability in time and year and illumination in the standard air photo supply?
I mean, generally with deep learning, yes. That's why it is so powerful and why people tend to use deep learning techniques for image detection nowadays over other methods, because it can handle that noisy data. I didn't try with many different capture dates, and although it would have variances in different image qualities feeding in. So yeah, I think it's better than the other things we tried anyway. And we'll find out more with a bit more testing.
Thank you. Why did you choose Google Colab over some Azure or AWS option?
It was free at the beginning. That was my main reason, and quick to set up. So I only, I think in between getting on the program and then having to start, there's only a few weeks. So I did have discussions around if I could use Azure or if I could use AWS. But I would have needed some kind of budget from somewhere, which would, yeah, then take a little while to sort out and set that up. And not having used either of those before as well, then that kind of barrier of learning as well. So Google Colabs was suggested by my mentor, as he's used it quite a few times, and yeah, you could set it up in a couple of minutes. In the end, I used a paid membership, so you can be a member for $8.99 a month, and for that month you get access to a 25 gig RAM GPU, which for the deep learning you do need a GPU to do that kind of analysis.
Thank you. And is there a way to automate the creation of the training data rather than manually labeling it, maybe feeding in results from the model with some manual adjustments?
That's a good, yeah, that's possibly a good idea. If you know that if your results are reliable, then kind of trying to feed them back into the model, but then you've got some added uncertainty from predictions going in as your inputs. I mean, the process of creating the training data was relatively quick. There's other ways of kind of outsourcing that effort, I guess. So things like using kind of online platforms to get people to kind of do that quick labeling for you could be one option, rather than doubling up your kind of uncertainty with added predictions.
Thank you. And what is Code Club?
Who said that? we have a code club in JNCC, which I've been running the last few years. Yeah, give me a shout. I can add you into it. So it's just a coding club every couple of weeks that meet and encourage each other to learn a bit of coding. We have training resources available and troubleshooting pages if you need help from someone with a bit more experience. Yeah, come to Code Club.
Very, very useful. I imagine, I'm going to pronounce this wrong, I imagine IDEA data might be useful for building forest quality models. LIDAR?
LiDAR.
LIDAR. I guess that's just a useful hints and tips there. And then question for both of you, are either of you aware of any progress in partnership with commercial data collectors for affordable access to higher resolution targeted data?
Yes, I'm aware of the kind of trials being run with Planet data. So there's trials with Welsh Government, and I think DEFRA Group are now getting in on it as well. That's the main one I'm aware of.
Thank you very much. And just one more question or point that's been popped on here. So is it worth mentioning that this is a unique approach being used across the UK, and we are partnering with countries who are interested in using this? Just a note from someone on there as well. Okay, so next slide on the Jamboard now. So questions for Georgina. Can you use historic aerial photograph and EO data to monitor changes in the condition and the extent of salt marshes as part of the deep learning process?
Yeah, you definitely can. It does depend a lot on the resolution of the data, because the older the data, often the worse the resolution generally. But there's been quite a lot of interesting historical studies that have done that. But deep learning does tend, for high quality data, you want high quality imagery. So you are sort of tied to more recent developments in terms of remote sensing, I would say. But yeah, you definitely can.
Thank you. And how did you choose which additional features to try and feed into the model?
I spoke to my mentor quite a lot, who'd done some previous environmental monitoring, but she was doing it more on detecting hard surfaces, where mine was vegetation. But so a lot of the indices I used were actually the same that she used, but for the inverse, I was looking for the inverse end of the scale. But to be honest, I just typed it into Google, good indices. I just typed it in and then just tried everything I could find, because it's not difficult to try and calculate them. It's just difficult to try and work out what's actually helpful. So it was a lot of trial and error, but I quite enjoyed it, so it was okay.
Yes, thank you. And Georgina, and so both of you might be interested. Oh, it's just updated and changed. Have you been in touch with the EA Geomatics team? The EA is about to publish and update a national salt marsh extent layer for England with some incorporated change analysis. Sounds useful.
Yes, I was aware of that actually, only recently though. It sounds really interesting. I've been speaking to Natural England a bit more about it than I have the Environment Agency. But yeah, hopefully if I can figure out what methods they've used, I can see if I can maybe work with them to develop the deep learning side of that too.
Perfect, thank you. Okay, so I'd like to thank you both very much. If anyone has any more questions, please feel free to get in touch with us and we can pass on to the presenters. This recording is going to be shared as well, so we'll send an update and email out